In June 1969, on a strip mining site outside Cumberland, Ohio, a machine rolled forward that should not have existed at all. Its designation was Bucyrus Erie 4250W, introduced after nearly 4 years of design and fabrication. Operators called it Big Musky, not because of marketing, but because nothing else in the pit even approached its scale. The archival brochure line was restrained, designed for maximum overburden removal efficiency. The numbers told the real story: a 220 cubic yard bucket, a total operating weight exceeding 13,500 tons, and electric drive motors drawing power directly from the grid. Trade journals at the time called it the largest walking dragline ever constructed for commercial use. Its boom cast a shadow longer than a football field. Each bucket pass moved more earth than a conventional excavator could in a full shift, and yet today the machine is gone. So is the company that built it. How does an engineering pioneer prove the future and still vanish from it? By the late 1910s, Bucyrus Erie was already a respected name in American excavation. It was the result of a 1927 merger between the Bucyrus Company of Ohio and the Erie Steam Shovel Company of Pennsylvania. The Milwaukee Works were turning out steam shovels that dug the Panama Canal, machines defined not by elegance but by uptime. Founders like Daniel P. Eales and later chief engineers focused obsessively on frame integrity and serviceability. Trades contractors trusted when downtime meant payroll bleeding. A 1923 Bucyrus catalog emphasized field repairable components, an early clue to the company's culture that would persist for decades. Dealers in Ohio and Pennsylvania pushed smaller shovels into coal and rail projects, building relationships before scale entered the picture. The company understood what contractors needed in an era when steam power and cable systems were familiar. The industry rewarded familiarity, not risk. Engineers worked in Milwaukee factory halls where the smell of cutting oil mixed with coal smoke from the foundry. Draft tables held designs for Class 14 and Class 20 shovels, modest designations for machines that moved earth one scoop at a time, cycle after patient cycle. In rail yards and mining camps, Bucyrus Erie equipment earned its reputation through thousands of operational hours, under conditions that destroyed lesser machines. Contractors learned that a Bucyrus could be repaired in the field with standard tools and locally available materials. This was not innovation, it was industrial pragmatism that kept machines working when replacement parts were days or weeks away. Trust was Bucyrus Erie's first asset, long before ambition became its liability. During the 1930s, Bucyrus Erie draglines like the Model 1150 became staples in Midwestern strip mining. Cable operated, slow and brutally simple, they required crews who knew tension, wear, and rhythm. Operators learned machines by feel, lever resistance, cable chatter, brake smell. A dealer manual from 1936 stressed predictable maintenance intervals, a selling point during the Depression when financing evaporated overnight. In the Illinois coal fields, machines worked 6-day weeks, pulling overburden back in passes that carved terraces into what had been farmland. The work was methodical. Position the machine, drop the bucket, drag it full, swing it back, dump the load, return for the next pass. Each cycle took minutes. Each shift moved hundreds of yards. Each season exposed new coal seams. Veteran operator Frank Kovach later recalled, "You did not rush a Bucyrus, you worked with it." The machine survived because they asked nothing unfamiliar. Cable drums turned, buckets swung, drag ropes pulled. When a hoist cable frayed, crews spliced it on site with tools they carried. The rhythmic clank of the machinery became the soundtrack of American coal production. The company survived the Depression by never asking customers to relearn excavation. Dealers stayed loyal because parts arrived when promised, and field repairs rarely required factory intervention. In hard years, predictability mattered more than capacity. A mine superintendent could calculate monthly output with reasonable accuracy because the machines delivered consistent performance. That consistency built loyalty across dealer networks and operator communities. By 1939, Bucyrus Erie had established itself as the conservative choice the manufacturer contractors turned to when the job required reliability over innovation. It was a reputation built one dragline at a time, one satisfied customer at a time. After World War II, coal demand surged to feed power plants spreading across the industrial Midwest. Bucyrus Erie expanded factory capacity and dealer territories, but the machines remained fundamentally conservative. The largest draglines grew heavier, not smarter. Engineers added boom length incrementally, reinforced frames with more steel, and upgraded cable specifications. These improvements enhanced capability without demanding operational changes. By the early 1950s, contractors faced a problem. Earth-moving volumes were increasing faster than labor efficiency. Utilities wanted guaranteed overburden removal rates to maintain fuel supplies for expanding electrical generation. Strip mines grew wider and deeper as near-surface deposits were exhausted, and mining operations pursued coal seams beneath thicker overburden layers. The math became unavoidable. Fewer machines needed to do more work, or mining costs would spiral beyond economic viability. Internally, younger engineers at the Milwaukee plant pushed for scale increases that went beyond incremental improvements. Patent filings from this period show not just boom extensions and reinforced bucket designs, but fundamental reconsiderations of drive systems and power delivery methods. Externally, pressure mounted from utility companies planning decades ahead. A 1954 trade report noted that mines were requesting draglines capable of sustained production exceeding current models by a factor of 2. The seeds of Big Musky were planted not in ambition, but in customer math. Power plants consumed coal at rates that demanded continuous overburden removal. Any interruption in the mining sequence created fuel supply risks that utilities found intolerable. The industry needed machines that could operate longer between maintenance intervals and move dramatically more material per operating hour. The problem wasn't innovation yet, it was volume. And volume, pursued without limit, would eventually demand a machine the industry had never seen and perhaps wasn't ready to support. In 1964, Bucyrus Erie engineers filed design studies proposing a fully electric walking dragline exceeding anything previously built. Internal memoranda cited reduced fuel logistics and constant torque advantages over diesel-electric hybrids that competitors were refining. A patent diagram from this period shows oversized synchronous motors driving hoist drums, elegant on paper, terrifying in capital cost. Chief project engineer George F. Wiseman argued that utilities could supply grid power cheaper than diesel. Fleets could burn fuel over a machine's operational lifetime. The logic was sound for a customer with transmission lines already crossing the mine. For Bucyrus Erie, it meant committing to a design with almost no second market. The 4250W would be purpose-built for Central Ohio Coal Company, financed through arrangements that tied the manufacturer's fortune to a single customer's mining plan. The engineering challenge was unprecedented. Design a walking dragline with a boom reaching 310 feet, capable of digging 180 feet below grade level, with a bucket that could carry loads exceeding 300 tons. No existing component catalog contained parts rated for these specifications. Everything would be custom: motors, cables, gear assemblies, structural steel sections, control systems. Even the lubrication system required engineering from first principles. Factory leadership approved the project in early 1965, allocating resources that represented a substantial portion of the company's engineering capacity. Design teams worked in parallel on mechanical, electrical, and structural systems, coordinating through weekly integration meetings where conflicts emerged and compromises were negotiated. The machine would not just dig coal, it would plug into the grid that coal powered, creating a feedback loop between energy production and energy consumption, risk and opportunity fused in a single schematic. Success would prove Bucyrus Erie's engineering superiority beyond any doubt. Failure would consume resources the company might never recover. Fabrication of the 4250W stretched Bucyrus Erie facilities to their limits between 1965 and 1968. Limits. Major components were built in sections at the Erie, Pennsylvania plant, then shipped by rail on custom flat cars to the Ohio assembly site. Custom factory records note welding challenges at steel thicknesses rarely attempted in mobile equipment. Some structural members required multiple pass welds with strict interpass temperature controls to prevent stress cracking. Welding. The The boom alone required 150 tons of structural steel, fabricated in segments that would be joined during final assembly. Boom! The bucket weighed more than many complete excavators of the era. It weighed 230 tons empty and was designed to carry 310 tons of overburden per cycle. Bucket. Each of the 4 walking pontoons measured 40 feet long and required hydraulic systems capable of lifting thousands of tons. Pontoons. Inside the Erie plant, arc weld, glare-lit night shifts as fabricators joined plate sections under engineering supervision that allowed no shortcuts. Night. The smell of hydraulic oil mixed with ozone from test motors running synchronization trials on assembly benches. Ozone quality control inspectors examined welds with X-ray equipment, rejecting sections that showed the slightest internal defects. Quality assembly crews worked around the clock as delivery deadlines approached, driven by penalty clauses in the customer contract that made delays expensive. Deadlines. Every design success increased the company's financial exposure. The machine existed now as steel and copper and insulation, components that would either validate the engineering or become the most expensive monument to miscalculation in the company's history. Financial engineers refined control algorithms while fabricators cut steel. Electricians wired motor controllers while structural specialists calculated load paths. The project consumed resources, attention, and reputation. Resources. By late 1968, major components were en route to Ohio. The machine would either walk and dig as designed, or Bucyrus Erie would face consequences that extended far beyond this single contract. Consequences. When Big Musky walked onto the Central Ohio Coal Company site in June 1969, it took days just to commission electrical systems and calibrate the drive controls. Operator manuals emphasized electrical discipline. Mistakes carried megawatt consequences that could damage motors worth more than houses. The machine drew power through a dedicated substation built specifically to handle peak loads during hoist and swing operations, with circuit breakers rated for industrial-scale currents. Trade publication Construction Equipment described the first cuts as methodical, almost ceremonial, with engineers monitoring every system parameter as the bucket bit into overburden for the first time. Operators noted smooth torque delivery, no diesel lag, no gear hunting, just constant electric force translated through cables thicker than a man's wrist. The bucket swung through arcs that seemed impossibly slow until the scale registered that each pass moved material volumes that conventional draglines needed multiple cycles to match. The walking mechanism advanced the machine across the pit floor with hydraulic precision, pontoons lifting and setting with mechanical certainty. Engineers had worried about ground pressure and stability on soft mine spoil, but the distributed load across 4 massive pontoons proved adequate. The machine moved in a rhythm: dig, swing, dump, return, walk forward, repeat. Each cycle removed another slice of overburden, exposing coal seams below. Within weeks, operators developed confidence in the controls. The initial caution gave way to operational rhythm. Production rates climbed toward design specifications. The massive bucket carved through overburden layers, clay, sandstone, shale, with impartial efficiency. Maintenance crews established inspection routines, checking electrical connections, lubricating bearing surfaces, monitoring cable wear. It worked, exactly as promised. The future had arrived on schedule, delivered by a company that had bet heavily on engineering excellence. The question was whether the market would reward that bet with enough additional orders to justify the investment. Big Musky could move over 39 million cubic yards annually under optimal conditions, removing overburden at rates that redefined mine planning. One bucket replaced small fleets. Maintenance crews adapted to electrical diagnostics instead of engine rebuilds, checking motor windings and relay banks rather than pistons and fuel injectors. The skill set shifted from mechanical intuition to electrical troubleshooting, from fuel chemistry to power quality analysis. By 1971, the machine had validated every performance projection. Cycle times held steady at approximately 55 seconds under normal conditions, faster than many smaller draglines achieved despite the massive scale. Structural fatigue remained within design tolerances. Engineers monitoring stress indicators found that the frame flex stayed well below critical thresholds. The utility connection proved reliable. Grid power was cheaper than diesel, exactly as Wiseman had calculated, saving thousands of dollars monthly in operating costs. But an economic echo was already forming. Fewer machines meant fewer purchases across the industry. Strip mines that might have bought 3 conventional draglines now considered one giant. Bucyrus Erie had solved the customer's immediate problem with such finality that it quietly created the manufacturer's long-term crisis. The logic was inescapable. If one machine could do the work of many, then mine operators would buy fewer machines total. Efficiency and repeatability, the very qualities that built trust, now worked against the business model that depended on equipment turnover. The machine performed flawlessly. The order book did not grow proportionally. Inquiries arrived from other mining operations curious about the technology, but few were willing to commit the capital required for machines approaching Big Musky's scale. The market wanted proof that the concept worked before ordering, but Big Musky was the proof, and watching it work did not require buying one. Excellence in execution created a demonstration that educated competitors while generating insufficient orders to sustain the pioneer. Photographs of Big Musky circulated globally through the early 1970s, appearing in engineering journals, trade magazines, and even general interest publications captivated by extreme machinery. The boom reaching across the sky, the massive bucket suspended in mid-swing, the scale made visible by tiny human figures near the base. These images became iconic representations of American industrial capability. Bucyrus Erie's name became synonymous with ultimate scale. Dealers used it as proof of engineering supremacy, even when selling smaller conventional models to contractors who would never need anything approaching that capacity. Sales presentations included glossy photographs and performance statistics from the Ohio operation. If Bucyrus Erie can build that, dealers argued, imagine what they can do for your application. But internally, capital was tied up in one-off giants, while production lines waited for orders that arrived more slowly than projections had assumed. The catalog grew heavier with custom options and special configurations. Sales engineers could describe machines for nearly any application, but standardization, the key to manufacturing efficiency, eroded. Each major sale now required significant engineering customization to match site-specific requirements. A 1973 dealer bulletin acknowledged extended delivery times due to engineering customization, a polite way of admitting that the business model had shifted away from production efficiency toward bespoke fabrication. Factory capacity sat partially idle between major contracts, creating overhead cost problems. Skilled workers faced unpredictable schedules. Engineering talent spent time on proposals that did not convert to orders. Prestige does not compound like volume. The company had built the most famous dragline in the world, generating publicity that money could not buy. But publicity does not pay wages or cover facility costs. The market wanted proven workhorses it could finance, operate, and replace on predictable cycles. Big Musky was proof of concept, spectacular proof, but converting that proof into sustainable revenue proved harder than engineering the machine itself. At peak operation in the mid-1970s, Big Musky validated every design assumption. Structural components showed expected wear patterns that confirmed the engineering models. Electric drives outperformed initial projections for efficiency and maintainability, with motor failure rates lower than anticipated. Operators developed deep familiarity with the control systems, reading instrument panels the way earlier generations had read cable tension and brake resistance. The machine became a known quantity, respected by crews, studied by engineering students, cited in technical papers on large-scale excavation. University programs in mining engineering added case studies on Big Musky to their curricula. Professors used it as an example of successful scaling principles, demonstrating how fundamental engineering analysis could be applied to unprecedented sizes. Competitors sent observers to analyze its operational characteristics from public viewpoints around the mine perimeter. Rival manufacturers studied the machine's movements, timed its cycles, photographed its configuration from every accessible angle. The design philosophy became transparent through observation, electric drive benefits, walking mechanism advantages, and bucket geometry optimizations. By 1976, Big Musky had removed overburden from thousands of acres, exposing coal seams that fed regional power plants exactly as planned. The Central Ohio Coal Company achieved production targets that would have required multiple conventional draglines. The engineering had been proven not just adequate, but exemplary, exceeding reliability expectations for such a massive and complex system. The future was demonstrated and now visible to everyone. That visibility would prove more dangerous than any technical challenge Bucyrus-Erie had overcome. Innovation, once published in photographs and performance data, and invites imitation from entities with resources the pioneer cannot match. Smaller firms prove concepts and larger firms scale production. This pattern had played out across American industry in automobiles, aircraft, and electronics. Now it was arriving in mining equipment, where Bucyrus-Erie's demonstration machine had mapped the path competitors would follow. By the mid-1970s, Caterpillar, Marion Power Shovel, and Harnisch-Feger Corporation expanded electric dragline offerings, incorporating lessons learned from observing Big Musky's operational success. These competitors introduced machines smaller than the 4,250W, but large enough to compete for the broad middle market, draglines in the 80 to 150 cubic yard range that utilities could finance more easily and deploy across multiple sites. Caterpillar's dealer network dwarfed Bucyrus-Erie's reach, offering parts availability and service response that smaller manufacturers struggled to match. A contractor in Montana could get Caterpillar parts within days. Bucyrus-Erie custom components might take weeks. Parts supply made a practical difference in procurement decisions. Marion Power Shovel, already strong in the mining sector, leveraged existing customer relationships built over decades of supplying shovels and smaller draglines. Contractors increasingly preferred standardized fleets with components on every regional parts shelf, reducing the risk of extended downtime waiting for custom fabrications. Fleet managers valued interchangeable parts across multiple machines, allowing them to cannibalize one unit to keep others running during emergency repairs. This operational flexibility mattered more than ultimate capability for most applications. Big Musky remained the most capable machine in its class, but its very uniqueness had educated the market about what was possible. The machine proved that electric drives worked reliably at scale, that walking mechanisms could be engineered for extreme loads, and that proper design could achieve cycle times competitive with smaller equipment. Competitors delivered that possibility in forms easier to finance and support. Innovation invited imitation, with scale advantages Bucyrus-Erie did not have. The pioneers absorbed development risk and market education costs. The followers leveraged proven concepts without the burden of being first. This asymmetry favored large, diversified manufacturers who could absorb initial losses while building market share, exactly the competitive position Bucyrus-Erie could not match. By the late 1970s, Big Musky remained unique, but uniqueness became a liability rather than a selling point. Financing tightened as interest rates climbed toward historic highs and utilities reconsidered capital expenditure strategies in an era of regulatory uncertainty. Mines consolidated under fewer corporate owners who preferred equipment standardization across properties to simplify training, maintenance, and parts management. One machine doing the work of many reduced replacement demand industry-wide, affecting all manufacturers but hitting specialist firms hardest. The dragline market matured, growth slowed, and competition intensified for a shrinking pool of new orders. Price pressure increased as manufacturers bid against each other for contracts that might represent months of factory production. Bucyrus-Erie faced a paradox. Their flagship proved that giant electric draglines worked brilliantly, but that proof commoditized the category. What had been a proprietary innovation became industry standard practice, available from multiple suppliers with varying advantages. Competitors with broader product lines and deeper dealer networks absorbed the market Big Musky had validated. A perfect machine became a market dead end when the very efficiency it demonstrated reduced the total number of units the industry would purchase. Engineering excellence solved the technical problem so completely that it eliminated the commercial opportunity for repeat sales at the scale required to sustain a specialist manufacturer. The market needed perhaps a dozen machines of Big Muskie's class globally, not enough orders to support ongoing development and production infrastructure. Excellence does not guarantee an ongoing business model. Bucyrus Erie had proven the future, but could not monetize that proof sufficiently. The company remained respected but financially vulnerable, dependent on sporadic large orders in a market increasingly dominated by competitors who treated draglines as one product line among many, not as the core identity requiring protection at all costs. The engineering was right. The business case was incomplete. Bucyrus Erie changed ownership in the 1980s as financial pressures mounted and the parent company restructured. Brand focus became diluted across product lines, which increasingly competed in commodity categories against manufacturers with greater economies of scale. The machines remained respected. Field performance was never the issue, but dealer confidence eroded as delivery times stretched and parts availability became less predictable. Competitors captured market share not through superior engineering but through superior logistics and financing options. Caterpillar offered lease programs and service contracts that reduced customer risk. Case and Deere provided equipment packages that bundled draglines with other machinery on attractive terms. Bucyrus Erie, with narrower product lines and smaller dealer networks, could not match these integrated offerings. Factory floors in Milwaukee and Erie saw quieter periods between major contracts. Engineering talent departed for firms offering more stable prospects and clearer career paths. The catalog still featured impressive specifications, but fewer contractors opened it when preparing bids. The reputation for innovation remained, but operational reality shifted toward survival rather than advancement. Big Musky kept digging in Ohio, accumulating operational hours that proved the design's durability even as the balance sheet weakened in Pennsylvania. The machine became a monument to a different era. Engineering excellence alone could once sustain competitive advantage before markets demanded integration, financing, and logistics at scales only diversified corporations could provide. The machine endured. The company did not. Success in engineering became failure in business when scale and timing misaligned. The industry moved forward, and Bucyrus Erie's independent identity did not move with it. Mergers and acquisitions consumed what remained of the original firm's autonomy. Big Musky was retired in May 1991 after 22 years of operation, its structural integrity still sound but the mine's coal reserves depleted and the parent utility shifting to other fuel sources and generation technologies. The machine sat idle for 8 years before being dismantled for scrap in 1999, its components too specialized for economical redeployment. The bucket was preserved in Miners Memorial Park near McConnellsville, Ohio, a relic of impossible scale open to weather and to visitors who could walk inside and contemplate the engineering ambition it represented. Modern excavators now use the principles Big Musky proved: electric drives for constant torque, walking mechanisms for stability on soft ground, and modular component design for maintainability. The engineering influenced an entire generation of mining equipment, even as the nameplate faded from active production. Every large dragline working today carries traces of lessons learned from Big Muskie's operational history. Bucyrus Erie's assets were eventually absorbed into larger conglomerates. The brand diluted and then discontinued as corporate identities merged and simplified. The company that built machines for the Panama Canal ended not with dramatic failure, but with quiet absorption. Its expertise distributed across successor organizations. The ideas did not vanish. They dispersed into industry practice, uncredited but persistent. A massive bucket, open to the sky, stands without the company that built it, a monument to futures proven but not owned. The engineering was right, the timing was not, and in the end, the ground remembers the machine, not the name stamped on the frame.